Hello and welcome to Ultralight Event Sourcing in Java Talk. My name is Andy Malakov. I am a lead solution architect at EPAM. Before we begin, what exactly is Ultralight Event Sourcing? I'm sure many of you enjoy outdoors and hiking. There is a hiking trend called ultralight backpacking. Going ultralight is a conscious decision to ditch some of the comforts, unburden yourself from all non-essential stuff, and invest into lightweight gear, train yourself, and then you can travel light, you can go faster and further. It turns out you can do the same with software. If you want to go fast, you may need to drop your comfortable Spring framework, your trusty Kafka and Spark, and go with high performance tools. During the next 20 minutes, I will share you our experience on this path. But let me do a 30-second introduction into event sourcing. Event sourcing is an approach to persist the state of the data in the system as a sequence of state-changing events. We work in financial domain, so our example here is about trading. Instead of storing current state of our business objects, and for trading systems this would be orders or investment positions, we store events that brought our system into the current state. This approach works very well if a state of our system is fully deterministic. So imagine we have an investment position of stocks and we want to open a new position in Tesla. We submit order request, we receive confirmation from our broker, and then let's say part of our order is filled by Nasdaq exchange. What is the state of our portfolio at this moment? Well, we own 15 Tesla stocks and maybe we will get 85 or more. As you see, instead of storing current state of order or current state of position, we can simply store a sequence of events that led into this state. How many times we updated orders? Order 3 times. How many times we updated position? Twice, when we opened position and when we got the first fill. So this gives us 5 database writes, but we only had 3 events, so event sourcing is the way to go. And plus, the fact that we have all the events recorded helps us to understand how exactly we got into the current state. And this will be the right moment to drop who we are slide. I'm a member of Deltix EPAM team, think tank, laboratory that spent the last 15 years building software for financial domain, specifically software products for quantitative research and trading. Our methodology is aggregate, analyze, act. Our products support aggregation of vast amount of market data, analytics and backtesting, development of trading algorithms, and ability to deploy these algorithms in real-time trading. Our clients range from small proprietary trading firms to banks and brokers. My specialization is market access and order execution. That is, I'm responsible for act in production side of our software products. Going back to conference team, you see most of my diagrams are black and white, so it was a bit of challenging to adapt them to that dark theme, but this one is an exception. Here we have a beautiful but somewhat naive diagram of our trading solution for broker dealers. You can find it on website cryptocortex.io. There are customer-facing services and apps here, user risk management, back office, and so on. This is a complex software system that took us years to develop. Ultralight event sourcing is used only where it matters, a subsystem that we call execution server or Ember. It is painted as a golden box on this picture. Does it mean it's special? Maybe. There are many other complex and important subsystems in this solution. But as you will see, Ember was probably the most expensive to develop per lines of code. And this slide is one of our customer stories. Here I must say that as a software vendor in fintech, we frequently find that clients prefer to remain anonymous. Let's call this client X. So client X is in market making business, which means they provide exchanges with liquidity. They keep the bids and offers on the market at all time. And here on the left we have Grafana dashboard showing us our system processing around 2,000 trading requests per second. Most of these are price adjustments. Typically, each such request is acknowledged by exchange, which generates an extra flow of around 2,000 acknowledgement events per second. And by the way, 2000 is rate limit of the market they are working on, not embers. This statistics here are shown for a period of about a month. And the little gap on the top chart corresponds to 6 hours during which target crypto exchange was down. So non-functional performance requirement and ability to update bids and offers with the smallest possible delay is critical for the business. The prices are usually tied to related financial instruments, and this information is very time sensitive. Our system writes every message to journal before processing. A load like this may produce around 5 gigabytes of journal data per hour, which is not bad for a system that is designed for latency rather than throughput. Speaking of latency, this slide shows tick-to-order latency numbers and how we measure them. For a benchmark like this, we simulate exchange activity using trading bots that we submit, that submit buy and sell orders to our matching engine. This gives us predictable and realistic simulation of real exchange. Bot configuration allows us to control market depths, how many buy and sell orders are active at any time, and the frequency of updates. Our system under test is shown on the right. Our product usually has a market data service that normalizes data received from different exchanges to universal format. We consume this normalized flow in trading algorithm running in Ember. Algorithm may react with buy or sell order, which goes to our order management system. IMS performs write-ahead journaling of each order before it is routed to exchange adapter if the order is valid. Outbound adapter converts message back to exchange specific format, and in our test we encode messages back to exchange specific fixed format. And what about the latency? So the latency is measured at network packet level using a libpickup packet capture library. This library taps packets at network buffer level and provides us with kernel timestamps. Once we correlate outbound packet, which is will be buy or sell order, with inbound packet, which contains a market data tick that signal that triggered the order, we get our tick-to-order latency. We collect millions of those measurements and build latency histogram like shown on the left. This specific latency numbers were observed at a rate of around 5,000 orders per second. And in this experiment, we deployed dummy trading algorithms that simply traded on every tick of the market, which is somewhat unusual, but fine for experiment like this. And this next slide shows us what happens if we increase order rate. This time, instead of using packet capture, we measure round trip time on the client. We use IPC-based messaging using our own library. More on this will be later. And as you can see, our current system is capable of processing around 250,000 messages per second in durable fashion. We do store each message before we process it. There is no batching of orders. And remember that trading systems are usually optimized for latency rather than throughput. What we can also see is that at a higher rates, our median and the 99th percentile even slightly improves. But as we approach higher message rates, our maximums reach 200 microseconds. We can also see some kind of funky batching effect at 100K rate. However, this 10K rate is order of magnitude more than typical client needs. Quick introduction into the notion of real time. Here we have a chart of showing us around 100,000 latency measurements. As you can see that median latency time is around 28-30 microseconds. And the red line shows us 99th percentile, which is around 85 microseconds in this case. What we can also see is that a significant number of signals took more than 100 microseconds or more. This slide is a better way to visualize what we're talking about, latency histogram. Let's imagine that our service level agreement requires us to process 99% of signals in less than 5 milliseconds and never spend more than 12 milliseconds on any event. This is shown by orange line. Non-real-time systems usually behave like shown by the red line. Yes, you will see that 99 and even 99.9% of signals are processed within SLA. But occasionally, a signal may experience a significantly higher processing time. Somebody may have an SLA of 1 second rather than 12 milliseconds. But the problem will remain the same. If your system is not real-time, sometimes signals take even longer than 1 second to process. Generic tools simply cannot guarantee you hard SLA. Is Ember suitable for real-time processing? Honest answer is, for some application, it can definitely be running under real-time SLAs. However, most of our clients do not require strict real-time. For them, it is sufficient that we can demonstrate significantly better latencies than common event processing systems. This is why the topic of this conversation is ultralight event sourcing and not real-time event sourcing. Let's start with a few simple examples that demonstrate what we are talking about. Imagine that your system contains many services that take considerable time to load the data from database or whatnot. Common wisdom is delay all expensive initialization. Let's deal with this when we actually need it. And maybe we get lucky and the data won't be needed at all. Seems like a wise approach. Well, not for real-time or latency-sensitive system. To get predictable response time, we just cannot be at the mercy of database query times. In our system, everything is initialized at startup. Next example illustrates typical path one has to follow to get the right gear. Let's consider approach to persistence. Some long time ago, we started with Hibernate, which was a great library to persist data into SQL database. This gave us good early start. But we quickly realized that we're just paying too much for convenience. So we switched to Spring GDBC. And then we considered Kafka for a moment, but ended up implementing our own message log for trading events. This gap, by the way, between traditional database storage and the journal or message log was huge. We had to rewrite our entire trading system along the way. And the point I'm trying to make is, if you want the best, sometimes specialized and custom code is what you need. Before we go any deeper, I would like to acknowledge one great source of design ideas. Over the years, we have been closely watching work done by Martin Thompson, starting from a disruptor pattern back in 2012, and more recent work on open source Iron library. We do use Iron for cluster messaging as well as transport option for Ember client API. If you haven't heard of disruptor or mechanical sympathy, please do look it up. Applied to the topic of this call, this mechanical sympathy principle can be stated as the following. You do not have to be a computer hardware engineer to write a fast code, but you do need to understand how modern CPUs and memory work. Okay, let's cut to the chase. This diagram shows us a central part of Ember. Let's start with CPU and concurrency related things. Ember runs a limited number of threads. IMS is a separate thread. Journal, Flusher is a separate thread. Trading algorithms, trading connectors, each run in separate threads. These threads do not share any data. They exchange information via messages that are transmitted via internal queues. We use log-free queues. We use single producer, single consumer queues where appropriate most of the time. And the main IMS uses multi-producer, single consumer queue. You can find similar data structures in Iron Agruno library. We use auto-generated message codecs that are optimized for in-memory data transfer, and all mission-critical threads are pinned to isolated physical CPU cores. These threads run in non-stop polling loops, and more on this will be coming later. So let me describe data flow in this diagram. Say we have a trading algorithm reading market data from exchange. And at some point, algorithm may submit a trade order. We journal it, and at the same time, we place it into IMS queue. Our IMS tracks order state, risk, and positions. If the order is valid, we copy it, order request into Exchange connectors queue. Exchange connector take it from the queue and send it to Exchange using Exchange-specific APIs. At some point, a connector will receive a field from Exchange. We communicate this field as order event, which we place in IMS queue, IMS will take this from the queue, update the internal state of orders and positions, and send a field back to the algorithm that submitted order. All right, so next important aspect is memory. Ember runs without allocating new object in hot pass. As a result, we don't incur garbage collector stop the world penalty. Even with the latest improvement, GC pauses can be measured in milliseconds, which is true for G1 in OpenGTK, to maybe hundreds of microseconds in continuous GC such as Zinc. To make zero GC policy habitable for our business logic, we usually rely on object pool pattern and flyweight pattern, and more on this will be later. So what's next? Our buffers use off-heap memory. Queues use CPU padding to prevent false sharing, and usually system operates in the optimal conditions when all business logic data fits into CPU cache. Our share nothing single writer principle of working with data helps us there. Few notes about network. As a system targeting beta latencies, we disable Nagel algorithm, TCP no delay. In our sockets, we primarily use non-blocking I/O. This allows us to process things in parallel. For local communications, we use Iron library. This gives us shared memory communications for collocated processes, or UDP for same network communication. In the cloud deployments, we configure Iron to use unicast UDP or use proprietary TCP transport. And as anybody in HFT, high frequency trading space, we played with TCP kernel bypass. So, well, this work has been done. However, none of our production clients use this technology at the moment. Still, it's worth mentioning this recipe in context of trimming down network latency of your stack. Okay, so next I'm going to talk about several design patterns that we use. This simplified code snippet illustrates how we run critical threads. Well, you can see that there is a loop, so each thread constantly polls input sources for new data. These are non-blocking calls. If data is available, it is processed immediately. Usually in small batches. For example, we may consume up to 64 market data messages before we switch to see if there is any trading messages to process. Well, if there is no data available, no market messages, no trading messages, we may start idling. Idle strategy may yield yet another to another thread or even sleep for a short time. However, in productions, our mission critical threads have empty idle strategy. This may give you 100% CPU utilization in monitoring software, so we have to rely on some other metrics to determine if Ember is overloaded. So with this pattern, all critical threads are always ready to process incoming data. Critical threads run on dedicated isolated cores, and we don't want to share this CPU with any other threads. We don't want operating system to take control. Price of context switching could be tens of microseconds, and combined with cache trashing, the penalty of letting somebody on our CPU could be just too high. Here's another design idea. Our order management system deals with hot data pass. All latency sensitive signals going through this pass, all latency sensitive system handled in main Ember IMS. In our previous architecture, IMS clients who would need to know current state would send a query to IMS. This frequently led to abuses where somebody would just fetch entire trading history from a process that normally deals with latency sensitive signals. Even if we impose query limits or paging on result sets, this may lead to abuses. So our current architecture, event sourcing architecture, allows us to replicate IMS state into satellite processes. Now we can service query-intensive clients from replicas. Furthermore, replicas may contain denormalized information or even index information. For example, we may stream trades to Amazon S3 and ask users to use Amazon Athena to query the data. And another benefit, satellite processes don't have to play by the same strict rules as mission-critical IMS. For example, code running in replicas can allocate new objects and involve garbage collection. This way, we can use third-party APIs, most of which do allocate new objects on each API call, for example, S3 client or JDBC client. And lastly, synchronous replication of trading messages allows us to run multiple Ember instances in the cluster. A follower Ember instance in this case has an exact copy of the leader. It runs the same trading algorithms and trading connectors. Algorithms on the follower node run in standby mode, where they are fully aware of a trading state but are not allowed to emit any own messages or talk to exchanges. And this is another frequently used pattern, flyweight. There are two places on this code snippet where this pattern is hiding: message producer and message consumer. This naive code simply places a buy order if market is low. So we have a market data consumer where we have a callback that notifies trading algorithms that something changed on the market. So this market change interface is, in this case, is a flyweight. So under the hood, we have a messaging framework that receives this data via in-memory buffers. We decode this into our data messages and present it under message change interface. If consumer, in this case this algorithm, needs to keep any information from this callback, it has to copy it. For example, here we initialize an order. And after we return from this callback, our framework is going to reuse this market change instance for the next call. And so the second is producer. So we can see that when we place an order request is another example of how we reuse one single object instance over and over when sending messages out. A call to MS immediately encodes order state into the queue, which means we could reuse our order request instance when placing the next request. Okay, so here is another neat feature that we use in our software. We call it counters. And this comes from the following problem: how could we monitor a mission critical process in a way that doesn't abstract its function? So if you use verbose logs, they're usually expensive, and any kind of periodic state polling is disruptive. God forbid we need to introduce synchronization around our state or embed micro web server or GMX agent to publish statistics. And remember that allocations are not allowed. So all these nice client libraries off limits. And metrics is something that we want to update rather frequently. So solution that we use relies on shared memory. Various Ember services write their metrics into dedicated area of memory mapped file. In some cases, even eventual write consistency for metric will suffice. And then we run a number of satellite processes that read this in-memory metrics and publish it somewhere. For example, we can display it, metrics in web apps or push it to Prometheus. This approach works under Docker and Kubernetes as well, where we use a single pod that shares volume with metric publishers running in separate containers. And we can hide all this complexity behind a simple API like shown here below. Typically, Ember thread pre-creates all counters at startup, and then on a hot pass, we simply call appropriate change method with negligible cost. I will put a link here at the bottom where you can find more information. We borrowed this idea from Arguna library. There are a few other things I would like to mention that illustrate what it means to go ultralight. Let's start with libraries. As I mentioned, we don't use databases. We opted for message log. We use in-house developed journaling library. In similar position, you can use Iron Archive. Fix protocol. Fix is a prevalent API that exchanges provide, so naturally we experimented a lot in this space. We started with optimized version of Quick Fix, ended up writing our own fix engine, and then replaced it with even better fix engine, which is now on GitHub. Also, we implemented our own garbage-free logging library, which is very fast. It's considerably faster than the GC Log4j, and I will put a link to it at the end of this presentation. We dropped Spring Boot framework. Main reason is that memory allocating proxies and unpredictability introduced by Spring Boot just was too expensive price to pay for our convenience. Data types. Java lacks adequate data type to represent precise money amounts or fractional quantities. If you have used a double data type in financial math, you know what I'm talking about. So we flirted with fixed decimal point for a while, found that 64 bits of a long data type was not enough to represent smallest price increments, for example, tickers like USD GPY. At the same time, we needed this data type to represent large money values, for example, money value of a large investment portfolio. Your mileage may vary. Our trading software supports all major asset types from equities to cryptos, futures. We figured out that fixed decimal point just didn't work for us. So for the past 3 years, we have been using in-house developed DFP library, decimal floating point library. This is essentially a Java wrapper around Intel implementation of EEE 754 standard, where money values, in our case, are base 10 floating point data type stored as Java long. I will put a link, GitHub link to DFP library at the end of this talk. So what else? We use flyweight pattern for textual fields. Java has a char sequence interface implemented by string. When we decode messages from binary data, what you will see in business logic is data buffer backed char sequence. And we realize that most text fields in our domain are ASCII text. So naturally we have optimized version of char sequence called ASCII char sequence or ASCII string builder. And here's another example. We call this alphanumeric 10 data type, which is essentially a short string that we can fit into long value type. Short text values are frequently used as human readable identifiers. For example, in all exchanges, traditional exchanges, are identified by so-called market participant ID, which is usually 3-4 letters long. For example, XCME. Here we have an example of like a crypto exchange, Coinbase, which we encode as alphanumeric 10. It has a length of 8, so we have 2 extra spaces left. And having such data type for textual field simplifies memory management. We no longer need to allocate string or use buffer-backed char sequence. We could use it as a key in our map collection, for example, store some per exchange information in long to object maps. This may sound extreme, but when you have a complete stack under your control, your fixed library supports it, your login library supports alphanumeric, your time series database supports alphanumeric. This is easy to use. So what else can we do? Can we go even more hardcore? How about exceptions? They're usually very expensive to trigger. Well, we do use exceptions moderately. We use them even on critical paths. We use singleton exceptions instances, which created during startup time with suppressed stack traces, but we do use them. How about polymorphism and overridden methods, cost of virtual calls and all that? How about it? What about recursion? It's we need a lot of stack space, right? Perhaps we should prohibit deep recursion. Where does this lead us to? Maybe we should advance towards FPGA or GPUs. Well, what we found is that we must remember the main reason we're building trading software in Java and not C++ or C or going to FPGA. The main reason is that we need to be able to write and adapt our business logic easily. And Java excels at that. So main idea of this talk is that ultralight, measured in tens of microseconds, event processing latency in Java is certainly possible. It boils down to applying the right design patterns and adopting clean coding habits. So if you're interested and want to learn more, please reach out to me at andymalakov@epam.com. I will be very glad. We have some in-depth presentation on the subjects available. Artem Korzun, our lead software engineer behind Ember, is looking for motivated audience. Please check out our open source projects. Some of the projects we built is now open source. This includes, by the way, Timebase, our time series database that Ember uses for market data delivery and custom messaging. And finally, here I have a link to our unofficial portal where you may find some technical articles and code competitions that our Deltix team is running. All right, thank you for watching. Goodbye.